Okay, so well, it's always great to be here in KL at Hack in the Box, and it's my favorite conference ever. So, end of the year, time is nice, relaxed, and always with good friends. So I hope you've been enjoying the show so far. What I'm going to talk to you for the next 1 hour is some R&D that I've done with browsers, and I began wondering as to what the hell is so wrong with browsers. I mean, there's many things wrong with browsers. Right? There's everything wrong with the internet anyway these days. But kind of figured browsers are becoming the next desktop, and there's a lot of things broken with browsers. So figured I should do something about it, and tinkered around and came up with a proof of concept tool right now called Teflon, and hopefully it should start some directions in building a better security model for browsers. So with that being said and done, a quick introduction about me. My name is Saumil Shah. I live in India and do a lot of security monkeying around. If you want to search, just Google Saumil and read up about stuff that I've done, if it exists on the internet. So what I'm going to talk to you about is, what are the next attack vectors for browsers? Thanks to the whole Web 2.0 nonsense, the browser is becoming the desktop of today. There's a lot of similarities and analogies if you start comparing browsers with desktops. I mean, you have a desktop computer, you download code off the internet and run it. Great, we don't trust it, right? We just, as long as it's free, we download it, we install it and run it. On a browser, it's the same thing. You point a browser at a website, stuff comes in and it runs. So what's the similarities and what are the next attack vectors on browsers? Now, there are classic attack vectors like cross-site scripting and whatever have you. We're not going to talk about that. That's all what I technically call user-land browser attacks. We're going to talk about hardcore browser exploits, stuff that blows up the browser and stuff that gets attackers control of your instruction pointer and so on and so forth. So with that, browsers, like I say, are the most fertile target area for exploitation. What makes browsers really juicy for attacks? Seen any average browser, you go to your aunt's place and look up, see what the browser looks like. Today's average browser looks like this. This is what it is. This is, everyone has like 80 different system tray icons and 30 toolbars and browser helper objects and all these. I mean, these make fertile grounds for attacks. You can blow up toolbars, you can blow up browser helper objects, you can blow up media handlers, you can blow up ActiveX objects and whatnot. And these are ripe with bugs. These are ripe with buffer overflows, with integer overflows or whatever have you. And all of a sudden, exploiting a browser has become very easy. And I'll show you later on that techniques like randomized stack or non-executable stack, they don't stop browser exploits. I mean, browser exploitation is a lot of fun. It's pretty swift and easy, and there's like new browser exploits coming out every week. Some of them are deadly, some of them are with some insignificant stuff. But before I get into that, let's think about what is at the heart of every browser. What makes a browser work? Inside every browser, there's like one central component. Anyone? Okay. It's this. It's a document object model, right? That's what a browser is. It's an HTTP client with a renderer. It loads in HTML and displays it on your screen. And it lets the user click around and make a new request and loads more HTML and displays it on your screen. That's what the damn thing does. Well, HTML displays fine, but browsers also have a wonderful little thing called JavaScript built into them. That's great. Now the software that I want to exploit has an interpreter at my disposal. I can program it before I can trigger an exploit. So what happens is you have a lot of user-loaded content through HTML, which comes and gets displayed and rendered on your browser. In addition to your DOM and JavaScript and HTML, browsers have many plugins. There's ActiveX, there's MIME handlers, browser helper objects, there's stuff like Flash, and now the whole environment is getting richer and richer. You have all this AJAX shit that's going around, various unaudited toolkits like Dojo or Scriptaculous, and they're being mashed up everywhere. And down below, at the plugin layer, you have the browser should be everything type of model, like Google Gears, Silverlight, Adobe Air. They want to make the browser access your host operating system, pull up databases, and make the browser stand alone. Well, that's great. That just made the exploit area very, very fertile. So if I were to compare the architecture of a browser with the architecture of any desktop operating system, it's very, very similar. You have stuff that happens in a browser and stuff that happens in a kernel. It's all the same. If we were to draw a diagram, we can draw something like this. The browser is analogous to an entire operating system. Your DOM layer and all your plugins in the browser are very similar to drivers and kernel. So, if I were to equate things, the DOM can be equated to the kernel. Your plugins and extensions can be equated to drivers. Now, what happens on a desktop if you exploit a driver? What do you get? You get control of the entire kernel. So what happens when you exploit a plugin on a browser? You get control of the entire browser. That's what happens. And on the userland layer, you have user-loaded code. The user-loaded code can access the kernel layer via system calls. And in the browser land, you have what I call the equivalent of browser layer system calls as these tags. You have the object tag, you have the embed tag, and things like these. Using an object tag, using an embed tag, you can reference any area. It's going to be hard to point, laser point as well. No, this is not going to work. Okay, using an object tag, oops. How can I draw? I can't draw. So, using an object tag, you can reference any plugin in the browser. You say object CLSID is equal to some COM component, it will load up the LinkedIn toolbar. You say embed source is equal to something.swf, it will load up a Flash player. Object file is equal to something.mov, it will load up QuickTime. So using these HTML tags, you can create code that references any drivers. Now what if this driver has a vulnerability? You can deliver the vulnerability entirely through through HTML and cause a browser to blow up. So that's what we're going to see. Here's an example of what I call as a browser syscall. Let's say you go to apple.com QuickTime, you want to see a lot of QuickTime trailers. There's HTML being loaded in. This HTML gets loaded in the browser's DOM and everything, that's fine. Inside this HTML, you have calls like, you have HTML tags like object CLSID equal to blah, blah, blah. This will load up the QuickTime player. You're trying to load up a QuickTime movie inside a browser. So QuickTime player will be loaded up and displayed in the browser. Internally, what happens, a QuickTime instance is created and runs in the same process context as the browser itself. So if QuickTime blows up, you get control of the whole browser. Now, exploiting a browser is pretty easy. You have many, many tools at your disposal. You can create a browser exploit entirely using JavaScript. So now let us say you want to break the QuickTime player through a browser. You want to send 100,000 bytes to the QuickTime object. You don't have to create a payload of 100,000 bytes and push it to the browser. You can create a little JavaScript loop saying instantiate a variable, pack it with 100,000 bytes, and then drop it on your own foot, and it will blow up the QuickTime object. What's more wonderful is you can preload the process memory exactly the way you like. This does not happen when you're exploiting other software. If you're exploiting a war FTP daemon, you can't say that load up 2 megabytes of knob sleds and shellcode in the memory and then go exploit yourself. With a browser you can. You can create JavaScript that loads up the heap memory exactly the way you like, thanks to guys like Alex and Mark and other researchers who worked on heap feng shui and stuff like that. You can spray the heap, you can load the heap exactly the way you want, and then let your exploit return to the heap. This makes browser exploiting a lot of fun, very easy. Techniques like address space layout randomization, non-execute flag on the stack canaries, these things don't bother us. What we can do is we can map the memory just in time and then jump into it. Okay, so quick theory on how browsers get exploited. Here's what you do. You have a little JavaScript loop with which you take large knob sleds, like 1 megabyte knob sleds, attach your shellcode at the end of the knob sled, and then make multiple copies of this knob sled and shellcode all over the heap memory using JavaScript arrays. And then you trigger your exploit condition. Your exploit takes control of EIP, but you can't return to the stack or anywhere else, so you say just jump into the heap, return to memory that was not initially there, but it's populated at runtime and things work. This is how most browser exploits work. So here's a quick summary of how it happens. Here's a diagram, rough diagram of the browser's process view. You have, let's say somewhere down in the stack you have an overflow. Before you actually trigger the overflow, what you do is you run some JavaScript in a loop and spray your shellcode blocks all over the heap. You spray multiple instances. You don't care where they are. As long as they occupy large regions of the heap, you can pick any address at random and straight away land in the heap. And that will work. So as long as you land in any of these orange blocks that you see on the screen, you're fine. Now once your heap is set up, you trigger your exploit, say overwrite a stack frame and overwrite a saved EIP or an exception handler and whatever it is. And instead of returning back to the stack as conventional exploits go, what you do is you jump into the heap. You return into one of these orange blocks and then you win. So that's the theory of browser exploits. We'll see a couple of examples, and then after seeing a couple of examples, I'll introduce you my research, the tool called Teflon, which is right now a browser plugin. It's implemented in Firefox, and it's my attempt to try and stop these kind of exploits from occurring. And then we'll talk about some pros and cons and features and limitations of Teflon and end the talk. All right, so now let's do some demos. Let me show you an exploit. I'll take a classic exploit. It's a Firefox and Windows Media Player exploit, a year or a year and a half old. If you have Firefox on Windows and you launch Windows Media Player with a very large file name, then the Windows Media Player plugin will crash and it will take Firefox with it. We'll see how we can create an exploit like this and then break it, and then we'll see how Teflon works and all that stuff. So, if time permits, we'll show another IE exploit. But everybody beats up on IE, so I didn't want to beat up upon IE today. Okay, here we are. This is my Windows VM, and we start Firefox. So there's Firefox. What I'm going to do is take a sample exploit code. Let me show you the code. Let's see what happens. Let me open up a more readable terminal.